Hi, this is Scott Wilkinson, host of Home Theater Geeks. On episode 29, I talk with Bob Carver about his 35 years as an audio and speaker designer. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CacheFly.com.
This is Home Theater Geeks with Scott Wilkinson, episode 29, audio legend Bob Carver. Hey there, Scott Wilkinson here with UltimateAVMag.com and HomeTheaterMag.com. Today's guest geek of the week is none other than Bob Carver, CTO of Sunfire and an audio legend for the last 35 years. Hey, Bob, welcome to the show.
Well, welcome. Thank you. Thank you. Glad to be here.
I'm sure glad to have you. I'm privileged, in fact, to have you on the show because, of course, I've known your name for as long as I've been interested in audio, and sure look forward to talking with you about all sorts of things.
Well, great. I've known my name longer.
as I'm sure you have. Listen, those who are tuned into the live video stream at live.twit.tv and logged into the chat room there, or at irc.twit.tv, can post questions for Bob, and I'll pass along as many as I can in between probably the too much that I have to talk with him about. But I sure do want to get some listener questions in there because I know there will be plenty of them. But let's start with your early days and your early interest in audio video. I was given a little heads up that your mom, Tina Carver, was actually an actress, a film and TV actress, I think, and you actually helped her prepare for scenes when you were a young child. Tell us about that.
That's right. Well, when I was very, very young, my mother and her actress friends would work scenes in the living room, and I would hold the script. And what was distressing for me was when they would practice and be having a fight, I didn't realize that it wasn't real. Oh my gosh, where did you get that?
Those who aren't seeing the video, we're showing a picture of Bob at a very young age with his mother, which was provided by one or another of your PR people. So I hope we're not embarrassing you too badly.
Not at all. Not at all. I don't remember it.
So anyway, go ahead and continue with the story.
Well, my mom was also a pianist, and my father was an engineer, so it worked great. My mom played the piano, so I had a little bit of music in my life, and my father was an engineer, and so I had a little bit of engineering and science in my life, combining the two, and where else could I light? A light, but audio.
Yeah, but then in audio engineering, yeah.
That's right, and so that was the very beginning. That was actually how I got started, I'm sure of it.
Yeah. In fact, your PR guy told me that you actually pretended to shoot your mom practicing her scenes with a film camera with no film in it.
That's right. Well, of course, we didn't have video cameras back then. They were real film cameras.
Right.
And the film went around in sprockets and holes and clickety clacked and
right. So you didn't want to do. Yeah, I understand.
Yeah, so I didn't want to use film.
Right. So later then in college, I heard about the story that you actually built subwoofers and amps for earthquake studies.
Ah, yes, for earthquakes. Seattle is an earthquake zone, so we have earthquakes here, and also we have the Boeing Airplane Company here in Seattle. Mm-hmm. So I built two of the biggest hi-fis, the biggest subwoofer for earthquakes, and a big, huge hi-fi set to make the sound of a jet engine taking off. My physics lab had a contract with Boeing, and my job was to build a big amplifier and a big set of speakers to simulate a jet airplanes taking off at about 100 meters.
Wow.
It was loud.
What kind of dB SPL were you getting out of that thing?
About 140. 140 dB SPL. At low frequencies, too.
Yeah. What was the low end of the frequency range you were testing?
About 7 hertz.
And you actually could build a subwoofer that would output 7 hertz at 140 dB?
Well, yes, but I cheated.
How's that?
I I used hydraulics. I used hydraulics to make the woofer go back and forth. And with hydraulics and a DC amplifier, it was relatively easy to make it go as low as we please. 7 hertz was the required cutoff, though. It was
7
fun.
hertz amp. You know, I've heard more than one person claim that we as human beings can actually hear well below 20 hertz, all the way down to 7 and below. Do you believe that?
Well, it's interesting. Our ear-brain system doesn't respond we don't hear it as a tone, but we hear it as something. We can hear our eardrums going in and out, but we don't hear it as a tone. We hear it as sort of an air pressure on our ears, sort of like going up in an elevator, something like that. But we can certainly sense it.
Do you advocate building subwoofers that can go down that low for home theaters?
It would sure be fun. Unfortunately, I think we would rock the house too much, shake the walls, rattle the rafters. And I've done that and had, in fact, when I was designing the first subwoofer, I was playing it really loud and the chandelier came down from the ceiling. Oh my God. Diana was furious with me. But I was happy.
Yeah, yeah.
As
now,
you
of
can
course,
imagine.
I can imagine, yes. As the true geek that you are.
Yeah.
Now, in college, of course, you didn't have a lot of money. None of us did. And I heard the story about building an amp in a Folgers coffee can. What's that all about?
Well, when I got out of college, I wanted to start an amplifier company, but I was broke. And so I couldn't afford a chassis. I couldn't afford heat sinks. But I was able to come up with a Folgers coffee can. I used that coffee can as the chassis to build the amplifier in. Also, I didn't have enough money, and I didn't have enough money to buy a transformer either. So I made it what we call a line-connected set. And so it just plugged into the wall. And of course, without a heavy power transformer, it didn't weigh much. It was very, very, very lightweight.
What did you use in place of the transformer?
The line, the transformer on the pole.
Oh,
there's a big transformer that feeds our homes, and it's out on a pole, and it belongs to the electric company. That's the transformer I used. It was a big one.
Much bigger than your amp needed. How much power did that thing generate?
Yeah, it didn't even raise a sweat from that. So that was my first amplifier.
And did you actually sell any of them?
No, but I used that amplifier to get a graph. In those days, there was something called the Macintosh Amplifier Clinic, and it was a race. The Macintosh Clinic would come to town. They would advertise in the newspaper, and we all like races. I mean, car races, boat races, and we even had amplifier races via the Macintosh Clinic. Everybody brought their amplifiers to the clinic, put them up on the bench to be tested, and would get a nice little graph of its performance. Mm-hmm. Well, oh my gosh, there's one. You are way ahead of me, that's for sure.
Well, I try to do my homework. Yes, we're showing on the video a picture of one of those graphs that came from the Macintosh Amp Clinic. And this is the Macintosh that we all know and love as the another preeminent high-end audio company, right?
That's right. In those days, Macintosh had a great reputation, and it was Bob who? Nobody knew who I was. I was a starving physics student. Right. So I took my coffee can amp, went down to the Macintosh Clinic, and had it tested, and I got a graph to die for. I was so happy that I got that graph.
And really what we're looking at here on the screen is what's important about this graph is that it's ruler flat right down at the bottom of the graph, indicating no clipping, no distortion, nothing bad happening. And they really pushed this thing hard, didn't they?
Oh, they did. They pushed it to the limit. They asked me how much power I'd like it to put out, and they tested it at power. And it was fun because what happened is there were all these wires coming out of the coffee can, and people were sitting around joking. What is this? What is this? Did you tune this wire for channel 7? Best reception in channel 7? And it went up and up. Now, you have to remember, most amplifiers in those days were 20, 30, 40, 50 watts. The Big Mac 75-watt per channel amplifier was among the largest amplifiers around. And they were heavy, too. Up on the bench. And Davey O'Brien, the Macintosh factory representative, would test them, and the local representative would help him, and they would go 75 watts. Well, I took my little coffee can. It didn't have a transformer in it, remember?
Right.
350 watts. And they didn't believe me. And they ran it up. The lights went out in the store. Got a new fuse in the lights, and finally got this graph. I made copies of this graph, and that got me started. I was in business with that graph. That graph said I had an amplifier that really did perform. I made promises of what it could do that were hard to believe, but there it was. Macintosh gave me the certificate that said it's real, and I was in business.
Wow. And how did you manage to squeeze out 350 watts of power out of this little lightweight thing? I mean, did it have to do with the fact that you were using the power company's transformer?
Yes, it did, but I didn't mention that.
So what's the basic story? How did that was really the answer to the question? Was you were using this gigantic transformer
that was out on the wall, on the pole, and I knew I could do it. I mean, I knew I could make this amplifier real with a real transformer and a real chassis, but I needed the opportunity. And that Macintosh graph gave me the opportunity. When I made copies of it and sent it out as a brochure, I don't remember how many copies, but thousands. And enough people believed me. Several didn't, of course. Lots didn't, perhaps, but that was how I got started, and that was it.
Now,
So
did you
transformer.
make actual commercial amplifiers based on this idea of not using your own transformer since then? I mean, not in coffee cans, but in real cases?
Well, I started out with using big power transformers of the sort that normally would be required to deliver 350 watts per channel, 700 watts because it's a two-channel amplifier.
Right.
And as time has marched on, I've always wanted to make a smaller, more powerful, lightweight amplifier. It's been a passion of mine my whole life, and that's what's evolved. And I now have smaller amplifiers and lighter amplifiers. I'll show you one right here. Mm-hmm. This one weighs 400 pounds, puts out 400 watts. I think it weighs about 8 or 9 pounds. But
Is that 400 watts in 2 channels or in monoblock?
2 channels. This is a 2-channel amplifier. Yeah. And this is what I used to start Carver Corporation with, this amplifier. So it's been fun. It's been a fun trip.
Boy, no kidding. We have a question now, as I knew we would, and in fact, it's a question I was expecting. Where can one get a classic Carver receiver or amplifier fixed? John has 2 that he needs repair.
Easy to answer. At Rita's Vintage Audio Repair. It's in the old Sunfire factory, and it's right here in Seattle, Washington.
Okay, and where would they find that online?
Rita's Vintage Audio. Just you can Google it, and I think it'll come right up.
Sure. Okay.
Let's see. I should know the address, but I don't.
That's all right. They can Google it.
Read it. Oh, wait a minute. 1920 Bickford Avenue. This is my push for Rita's Vintage Audio. 1920 Bickford Avenue, Bickford, in Snohomish, Washington. It's right next to the Sunfire factory.
Excellent. Excellent. Another one interesting story that I was told in preparation for your appearance here was the Amplifier Challenge, which was, I think you issued it to magazines, right? Or did they issue it to you? I don't remember. But the challenge was for you to replicate the sound of certain amplifiers such that an A/B test by seasoned listeners would not be able to tell the difference.
That was a lot of fun to do that challenge and to pull it off. It came about because a magazine was questioning my ability to make an amplifier sound as good as a vacuum tube amplifier. A big, expensive vacuum tube amplifier, especially since I was selling modestly priced, very powerful amplifiers. That article, interestingly enough, has survived for, I think, over 20 years, easily about 20 years or more, and it's been published in so many languages around the world, and I can't believe that story has had the staying power that it has. But it was a great challenge, and I won because I made my inexpensive amplifier sound like a $1 zillion vacuum tube high-end amplifier, and nobody could tell the difference.
Yeah, that's incredible.
So,
we were showing the cover page there of the Stereophile article on it. I think Audio Critic was the other magazine.
That's right. Audio Critic and Stereophile did it for both both magazines.
Right, and your job actually was to replicate the sound of a Mark Levinson ML2 in the case of Audio Critic, I think, and Conrad Johnson Premier 5 in the case of Stereophile. So how in the world did you copy or emulate or simulate or replicate, any word you want, the sound of these amps, which I think are tube amps, are they not?
That's correct. Or at least the Conrad Johnson's a tube amp, yes.
So how did you do that with an amp of a very dissimilar design?
Wow. What a question. I'll try to do it in 100 words or less. What I did is I went to a hotel room, ensconced myself in the hotel room, locked the doors, pulled down the shutters, took in this tube amplifier. I had my scopes, my meters, my wires, my decade resistance boxes, my calculators. I had everything in that room that I needed. I measured everything I could think of measuring for the vacuum tube amplifier, the Conrad Johnson, characterized what an engineer would call its transfer function, which just simply states the change that the signal undergoes as it goes from the input of the amplifier to the output of the amplifier. There's a black box. The signal changes somehow as it goes through the amplifier. That can be expressed in terms of mathematics. And so once I had the expression for the transfer function, all I had to do was replicate that transfer function in my solid state amplifier. If I succeeded, I could make a simple measurement at the end, which involved connecting a speaker across the two amplifier terminals. If the signal from microsecond to microsecond was identical, in other words, here's one amplifier, here's another amplifier. If the signals are not the same, there'll be a different signal, and you could hear it. If the amplifiers are identical, the two signals will be in synchronism, like this. The output the difference between the two signals will be zero. The speaker will be silent. And so that was the ultimate test to see if I was successful. And when I put the speakers across the amplifier terminals, there was nothing to be heard. It was silence. Even though there was a raging volcano inside of each amplifier in terms of Beethoven and rock music and everything else. It was fun.
And then another part of the test, of course, was having the Stereophile guys, listen to the two amps in a blind A-B kind of way and see if they could tell the difference. And they couldn't, could they?
That's right. They couldn't. Well, they could 50% of the time.
It's like saying a stopped clock is correct 2 times a day. That's exactly better.
That's right. That's exactly right.
Better than one that loses 5 minutes a day. Keeps better. A stopped clock keeps better time than one that loses 5 minutes a day. We got here a question from SoCal Ray Jr., who asks, "What gave you the idea for long excursion subwoofers?"
What gave me the idea for long excursion subwoofers? That's a great question. And it was an eviction notice from my living room. Diana said, I had huge subwoofers in my living room. She said, and I wanted more, of course, because I wanted more bass.
Who doesn't?
So, yeah, well, I did. There's part of me that wants more purity of mid-range and high frequency, purity of essence, but I really want more bass. So she said, you have to move, you have to get all your stuff out of the living room. Now, I'd been there for a long time with wires and scopes, and it was her turn to have the living room with pictures and flowers and nice things. So I agreed, and I said, sweetie, if I can make a subwoofer that's very small, can I stay? And she said, no, it has to be invisible. So I said, what? It has to be invisible? That's a little severe, isn't it? So that night, I went to bed, and I was thinking, how can I do this? And I knew that it had to be about this big, or it had to be very small. So I thought I knew how to do it. I woke up the next morning, mocked one up, and I didn't have it working yet, but I knew I could do it. At least I thought I could. So I called her down, I put it behind the flowers, and I said, I made a very small, invisible subwoofer. And she looked around the room. Now, to me, I knew where it was. It was behind the flowers. And I saw it blinking with a bright red light in my head. But she didn't see it. She said, it's truly invisible. And all it was hidden behind the flowers, behind the ferns, actually, in the living room. So it turns out that if you, to come back to the question, the scientific component of the question, if you shrink the subwoofer down and make the driver have a small diameter, it has to have more excursion. The amount of bass that comes out of a speaker is equal to the bore times the stroke. It's the cubic inches displacement, just like a car engine, bore times stroke. So if you make the bore small, because you want to make it small, it has to move back and forth more to have the same air moving ability. And it turns out when you make the woofer small, it makes the air pressure in the box so high that it's hard to push the woofer back and forth. And that was another scientific challenge that I had to overcome. And
isn't that overcome by porting the box, venting the box?
No, actually porting the box. It's porting the box. If you have a port in the box, when the woofer moves in, the air in the box moves in, and when the woofer moves out, the air in the port also moves out. So they're in phase with each other, and the pressure in the box is enormous. I know what you're thinking, that if there's a port in there, the box pressure can drop because the woofer moves in and the air moves out. But it doesn't work that way. It works like a slinky. If you take a slinky and move a slinky up and down, if you look at the slinky, as you're moving your hand up, the bottom of the slinky is going down. And when you move your hand down, the bottom of the slinky is coming up. It's only if you go very slowly does the slinky and your hand go up and down.
The two ends are in phase, yeah.
That's right. The two ends are in phase. So actually they're out of phase. The two ends are out of phase because one's rarefying the pressure and the other's making the pressure positive. But it turns out if you take one of my subwoofers and push on the cone, it feels like you're pushing against a brick wall and you're pushing air pressure inside. And I can remember taking it to a reviewer for the first time. Reviewers were so used to putting their fingers on a cone and pushing it in and seeing how easily it moved back and forth. And if it moved silkily and easily, that must be a great woofer. It's going to have lots of bass. And when I brought mine in to the reviewer, he pushed on it and he couldn't budge it. And he didn't think it was going to move. He thought it stuck, but it wasn't. It didn't. It moved violently. There was a hurricane in that box, but outside of that box, it just made bass. So it was cool. Yeah.
Now, do you use a ported cabinet for your subs or sealed?
They're sealed, but they have what's called a passive radiator, and a passive radiator has the same mathematics associated with it that a ported system does. Although it works differently. There are two woofers in the box. One of the woofers has a voice coil and is powered by the electric motor, by the wires and the magnet and the electricity that's going through the wires. It makes the woofer move.
The amplifier and so on.
That's right. The passive one, and the force on that wire is given by an equation called the force is equal to magnetic field intensity times the length of the wire, okay, times the current that's going through it. F is equal to BLI, remember that. This is the only equation I'm going to talk about, I promise.
Hey, this is Home Theater Geeks. We can get geeky. Go for it.
Okay. Oh, great. My kind of audience, geeks. So, I love you guys. I love you women. I love you all. Moving right along to the passive. The passive radiator has a giant weight on it. In fact, I've got a weight around here someplace, but it's a 2 or 3 pound weight. And if you remember from high school physics, there's a force associated with accelerating a mass. F is equal to ma. Force is equal to mass times acceleration. So the active driver has force equal to B, L times the current. The passive driver has a force equal to mass times acceleration. And their motion, they're on the opposite side of the boxes. The motion is like this. I don't know why it's called a passive. It's anything but passive. I mean, that F equals to ma force is enormous. It's over 200 pounds on some of our big woofers. So if you put the woofer on the ground and stand on it, and if you weigh less than 200 pounds, actually, I think it's about 180. So you have to weigh less than 180, and it'll bounce you up and down.
I guess it's passive in the sense that it's not being driven by the amplifier, by the electronics or the electrical current. It's just reacting to air.
Yeah, that must be the reason.
So a passive radiator needs to typically be opposing, on the opposite face of the subwoofer than the active driver, correct?
Well, it depends on which side of the box it's mounted on. Basically, it has to when they both move, they need to both push air or compress the air in the room, and when they go the other way, they have to both be rarefying the air. And they can move like this, that would do it if they're on opposite sides of the box, or if they're on the same side of the box, they have to go like this, back and forth. In any event, both of them, they're always compressing the air.
Understood.
Out. Yeah.
Great.
That's the way they work.
That's what. Yeah. Okay. I always thought that for subwoofers, the larger the diameter of the driver, the better, the lower it can go, and so on. But you've just demonstrated that that's not necessarily true. That it's the volume of air, and so if the driver is smaller, it just has to move farther in and out. That's a new or a clarification that I appreciate.
And there's another step that's really important. It turns out that the efficiency goes up as the driver goes down. The efficiency of the system increases when you make the driver smaller. This is non-intuitive, and sort of nobody believed me when I first said that. But when you do the mathematical analysis, the efficiency is proportional to something called the back EMF. And the back EMF is related to how fast the voice coil is moving in its magnetic field.
EMF stands for electromotive force. I just want to make sure everyone understands that.
Exactly.
And what is the back EMF?
The back EMF is this electromotive force, the voltage that's produced if you have a motor spinning without putting any electricity into it. That's when a motor's spinning around by inertia, it makes electricity. When you speak into a microphone, it makes electricity. You can work them either way. You can put electricity in and get motion out, or you can put motion in and get electricity out. It's reciprocal. But if you have a small driver that's moving back and forth farther than a big driver that's only moving a little bit, it's moving much faster because it has to travel farther in the same time period. Let's say it's producing 25 hertz. If it's going like this 25 times a second, obviously it's moving faster than if it's just going like this 25 times a second. And it's the speed squared that develops the efficiency. So the conventional wisdom that if you make this woofer small, the efficiency would drop and would require, if you made the box 10 times smaller, it would take 10 times more amplifier power to make it run. And that's true. That's very true in conventional driver design. And so what happens is if you shrink the box and drive it hard enough to make some sound, you end up making a little voice coil in there glow red or glow white. So if you have pinholes in your woofer, you have little beams of light coming out and lighting up your ceiling. You have a free planetarium, but it doesn't last very long because it's white hot.
Right,
so
it'll soon melt.
That's why it's important to get the efficiency up.
Right, like the Krell metal in Forbidden Planet on the door when they finally break through.
That's exactly right. That was made out of adamantine steel.
There you go. There you go.
I think.
Well, listen, SoCal Ray also asked a question that is absolutely on my mind, too, which is, can you explain your sonic holography technology?
Oh, boy, I love sonic holography. That was a killer product. But here's how it works. When, let's see, when we listen to real life music, real live events, for each single sonic event, we hear two sound arrivals. The sound, one for each ear. So for every single event, we hear two sound arrivals, and our ear-brain system in our head makes sense of that. It builds acoustic space. It builds, I hope I wasn't jiggling the camera too much. There we go.
There you go.
And it builds a sense of acoustic space, and it allows us to understand the real world out there. When we play that back in two-channel stereo, unfortunately, for every single sonic event, we hear 4 sound arrivals, 2 per speaker per ear. That's 4, not 2. 4.
So something coming out of the left speaker, we hear 2 events, one in the right ear, one in the left ear, and similarly with the other speaker. So 4 sonic events. I'd never thought of it that way. That's fascinating.
And what that does to us is our brain doesn't know what to do with that, because we evolved over an evolutionary period of adaptation, millions of years, to only process 2 arrivals for each sonic event. So 4 just confuses our hearing system, and the image collapses to a flat curtain of sound between 2 speakers. That's actually what happens. It's sort of like Egyptian cave drawings or Egyptian art. It's very flat, and yet we can still enjoy the music, we can enjoy the tonalities, we can enjoy everything, except it's sort of a flat curtain of sound. I talked with
John Atkinson about this at one point during our podcast. He's the editor of Stereophile, about how experiencing a live performance, a live musical performance, can never be exactly the same as experiencing it on a 2-channel reproduction system. And this may be partly why.
That's absolutely in large measure why. It's not the whole, and nor is it the entire reason. However, if we want a live recording to play back in our living room and sound as close to real as possible, one of the things we have to do, this is a necessary but not sufficient condition, of course, is to get rid of those 2 extra arrivals. Because if we get rid of the 2 extra arrivals, what we're left with is the original 2 that nature intends us to listen to build the soundscape in our mind's eye. So, what sonicalography does, it's very clever. This left speaker launches a sound which travels across space to our left ear. Unfortunately, that same sound travels to our right ear. That's bad. The left ear is good, the right ear is bad. So, sonicalography launches in just the right way, in just the right moment, at just the right phase, an additional sound that travels across space and cancels the one that came from the wrong side speaker. And by canceling the sound, what's left is the sound that arrived to the left ear. And
so you're saying that the right speaker needs to launch something of what the left speaker is doing, but in a phase and delay relationship that cancels what's getting into your right ear.
That's correct. That's correct.
But then doesn't that one also reach your left ear as well?
Well, you have to have another cancellation signal for that one. And it goes on.
Doesn't that go on infinitum?
Ad infinitum. Fortunately, as a practical matter, you don't have to cancel a lot of them, just enough to mostly get rid of that other sound. And what happens is the sound takes on a large. The sound can go outside of the speakers. It goes to the left of the speakers, to the right of the speakers. It goes higher than the speakers. It goes far back from the speakers. And I remember my first demonstration at the show. One of the demonstrations I did was I had a cup of ice water, and I had it jiggling around, and it was coming out of a pair of speakers. And then I turned on the sonicalography, and the people who were watching it, and interestingly enough, they had to be in a line between the speakers, so there's a line of people, and the water jiggled in your ear, and people thought, I'm going to get cold water in my ear. Because the sound, I mean, think of it, the sound of the water jiggling on the left ear was canceled. And so that's what, if you hear sound in just one ear and one ear only, that means the sound's very close to that ear. So
do you still offer sonicalography in your products to this day?
Yes, we do. What's happened? Since Dolby has come out, Dolby came out after sonicalography, and surround sound has really taken over where sonicalography used to live. Sonicalography is still lives happily in 2-channel systems, and we have audiophiles today that really enjoy 2-channel systems, and the phase and depth information and the cues that a 2-channel system can deliver makes it really worthwhile to have a two-channel system for many people, for many of us. I'm one of them. I love two channels. And I love multi-channel as well, but I really love two channels. There's yeah.
So, we got a follow-up question from SoCal Ray, who says, is this only for two-channel, or does it work with multi-channel? I would assume not.
Well, yes and no. It depends. That's the answer. It depends.
Of course, as always.
Yeah. Sonic holography works on the front hemisphere. So
Right.
it makes the front hemisphere large and deep and high and wide, and the rear channel speakers and the side channel speakers fill in the back. Sonic holography only does the front hemisphere. So from that perspective, yes, it does. However,
Okay.
for the most part, surround sound is mixed in a way that doesn't include sonic holography. So the mix down is what the engineer and what the recording artists and what the mix down artists wanted. So,
Except that it's applied after the mix, right? It's applied as post-processing in the user's system, right?
that's right. And since it's applied post-processing, you have to hook it up, push the button, and decide if you like it or not. But it always, to me, it always enhances the realism.
Now, an outsider, the outsider here asks, so listening with headphones, is that more accurate than even the two-channel listening, putting aside sonic holography for the moment?
No, it's actually not as good. And the reason for that is a subtle one. If you have an earphone on, the sound that the earphone makes, the sound goes into your ear and it bounces off your eardrum. It comes back out and it bounces off the ear cup diaphragm, then it goes back into your ear, bounces off your eardrum, and it goes back and forth, and it makes a lot of sound arrivals, not just one. It makes a multitude of sound arrivals, and each one of those makes the field collapse.
Wow, that's amazing. I'd never thought of that before.
Well, I was trying to make a pair of headphones, and I ended up with a pair of headphones that didn't have that reflective quality, and it was tough. I had my ear cup on a long tube with a lot of sound absorbing material inside. I had to play it at enormous levels with lots of equalization to get it to sound right, but it did work. At that point, I had a pair of headphones that would allow our hearing mechanism to hear the correct number of sound arrivals so our ear-brain system could process it and build a big sense of acoustic space.
Yeah, but talk about looking like a dork. I mean, what, you got, how long were these tubes?
They were about 1 meter long. But the thing is, I work
You have
in
these
my
things
lab.
sticking out 3 feet from either side.
Yeah, I know. I did look like a dork, but I didn't mind. I put the shades down and locked my door and didn't let
Yeah,
anybody-
okay. All right.
Just a moment. I have a note being handed to me.
Oh, yeah, sure. Please, go right ahead. Bob is getting something behind the curtain.
Yeah.
What do you got there, Bob?
Pardon?
I thought you were getting something to show us.
No, I was just reading a note that was handed to me.
My apology. Okay, our engineer is asking about those speakers behind you, and I was going to also. I know that you're a big advocate of ribbon speakers, so talk to us a little bit about ribbon speakers and what is that sitting behind you?
That is a ribbon loudspeaker. It's called the Amazing Loudspeaker. And I called it the Amazing Loudspeaker because I wanted to give it a name that aggrandized it whenever we spoke.
Nothing better than calling it the Amazing Speaker, then, I think.
I know. I thought it was better than calling it the RB17-3.
Yes, thank you very much.
Some forgettable alphanumeric number.
Right.
I've always liked, a long time ago, when I learned this at Harry Pearson's house. Harry Pearson is a reviewer, and he wrote a treatise years and years ago about how to listen to soundstage. I was just an infant. Oh, not quite an infant, but I was a young man then, and he influenced me a lot. I remember being in his house and listening to these big planar loudspeakers. They were genuinely captivating. And they work. They actually develop and deliver a large, believable soundstage with nice imaging inside that soundstage, actually stunning imaging inside the large, believable soundstage. They work basically because they're dipoles. They throw a sound out the back as well out the front. The sound travels across the room, bounces off the back wall, and comes back again. Now, when we hear two sounds instead of one sound, if it's inside the interaural time delay, that is, if it doesn't take much longer than the go between our two ears, which is about a millisecond or so.
Yeah.
If it's longer than that, it sounds great. Echoes sound good. We believe them. They make the sound stage sound big, sound lush. And so these planar speakers influenced me a lot. And I decided I was going to make one. And I could make it an electrostatic one, or I could make a ribbon one. One makes the diaphragm go back and forth by electrostatic attraction and repulsion, and the other is a magnetic one. That's the ribbon. I chose the ribbon one, and this is the ribbon loudspeaker that I designed. Behind those panels are 4 big 12-inch drivers to make the bass.
I was going to ask you about that, because I've never seen a ribbon or a planar speaker that could really go down low. You need dynamic drivers to do that, right?
Yeah, that's right. Those are their dynamic drivers behind that. They start around 100 hertz. And
are they actually behind the ribbons and pushing sound out through the ribbons?
No, they're immediately behind the grill cloth. They're the black grill cloth.
Oh, I see.
There are 4 of them from top to bottom.
Okay, so those are the bass units that are sitting behind you, actually.
Those are the bass units.
And then the ribbon speakers are separate. Oh, no, I see them. They're the little tiny things there.
Yeah. They're about 5 feet tall. The ribbons go from the bottom to the top. Now, those speakers, I had them in black, and they were called the surfboards from hell. When multi-channel arrived, we couldn't put 5 or 6 of those speakers in the living room. They would dominate it. So the requirement was that somehow I make a little baby one. Another eviction notice from my wife. So this is a speaker that superseded the big one, the big amazing behind me. And
look at that! Wow.
Yeah, it's a little baby version of the ribbon. There it is.
I understand the ribbon actually is folded on itself several times. There, we can see it.
There. Can you see it now?
Yeah, hold it up to the camera. Yeah, I see.
There.
Now, is
Thanks,
that
I'm
true
glad you
that
said
what I
hold it
heard
up
that
to
the
the
ribbon folds around itself several times?
The ribbon, the way it works is that ribbon is about from floor to ceiling, and it's 5 feet tall, and the output of a ribbon is related to the length. It's again IL cross B. Now, oops, I promised I wouldn't say another equation, but there I did.
It's okay. We're all geeks here.
So this ribbon, I took an X-Acto knife and I slit the ribbon, that big long ribbon behind me, and I cut it into little tiny strips, and then I folded it. It was 20 feet long, and I folded it around and around and around and around and around and around and around until it fit in this little box. And if you look carefully, I don't know if you can see it on the television monitor, but if you look very carefully, you'll see that it's many, 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 many turns of very fine ribbon material. And that way, this ribbon in the little speaker is as long as the ribbon in the Amazing. So it has the same output, even though it's a little tiny speaker. And it has side-firing woofers that make the big sound field that I talked about a minute ago. The long-term arrivals arise because of the side-firing drivers. It makes a big sound stage.
Now, are those folded ribbons also open on the back to be dipoles?
No, these are not. This ribbon is designed to just fire forward without being open on the back. And to get the big sound stage that I wanted, I had to have 2 drivers, one on either side, which takes the place, more or less, of the sound coming out of the back. It takes the place in a different sort of way, but it builds a big sound stage.
And don't those drivers also take care of some of the lower frequencies that the ribbons can't really handle?
That's correct. The woofers on the side of this go down to around 100 hertz, and then a subwoofer takes over, and they go up to about 400 hertz where the ribbon takes over.
You said earlier that you chose ribbons over planars, which are big sheets that are vibrating in a dipole fashion. Why is that?
Well, I built prototypes of both. I actually built both to teach myself which ones would be more desirable. And I concluded that the ribbons, I liked the sound of the ribbons better for a variety of technical reasons. So I went with the ribbons. Also, they didn't require the extra complexity that a regular electrostatic diaphragm requires. But they both can sound beautiful and just great. And there are lots of us audiophiles that follow ribbons, magnetic ones, or planar electrostatic speakers. Yeah.
Let's see. Razor65 asks your opinion about Class D amps.
Class D amplifiers. Wow, what a question.
I was going to ask you that one too. I got a great chat room here.
I remember the first Class D amplifier I ever saw was from Bose. And when I had just started Phase Linear, Bose came out, advertisements, and he said, we have a new amplifier coming. Good things are worth waiting for. And he had a big rug over it, so you couldn't see it. And month after month, he was running the ad for his new amplifier. I was scared. I was just starting Phase Linear. And I thought, uh-oh, I'm out of business. I mean, Bose knows what he's doing. I'm going to be out of business. He's coming out with a Class D amplifier, and he knows what he's doing, and I'm doomed. And then when he brought it to the hi-fi showrooms to show it off, I looked at it, and I was overjoyed. I'm not going to go out of business because of this amplifier. I was so happy. What happened is Class D amplifiers didn't sound very good. And the early ones were big. Now, as time has marched on, a lot of very smart people have worked very, very hard and very diligently and have created ever smaller and smaller amplifiers to today. And oh, by the way, let me backtrack just for a moment. Every few years, I would have the sense that Class D amplifiers are finally here. Finally, the sonic problems have been overcome, and finally, the reliability problems have been overcome, the switching speed problems have been overcome, the RFI problems have been overcome, and next year we're going to see switching amps make inroads. Well, it turns out, even today, we haven't. When we listen to Class D amplifiers, most of us who listen don't think they sound quite as good as a full-blown analog amplifier. And there are a variety of reasons for that. Again, I'm going to say right around the corner, in the next year or two, we'll have Class Ds working. Now, I've been saying that, my gosh, for 30 years. Infinity came out with one. Arnie Nudell came out with one called the Swamp Amp. I don't know what Swamp stood for. Switching amplifier, something like that.
Bang & Olufsen's Ice Power is gaining a lot of traction. A lot of companies are using that in their full range amps.
There is at this point, there's no technical reason, only some artistic reasons in the final implementation of a switching amp that they should be successful now. They really should. They should.
But you don't make them yet.
Not for stereo listening. The switching amps we do make are for the subwoofers.
And I've heard that they are, in fact, pretty well suited for low-frequency amplification.
That's right. That's right. They're ubiquitous. Everybody uses a switching amp for their subwoofer, literally everybody. And that's where their strength lies right now. It's the nuances of the upper mid-range and the high-frequency components and music program material. Switching amps seem to fall down right now.
So how do your switching power supply amps differ from Class D?
I cheated, once again.
Of course.
Yeah. The switching power supply supplies the power for a Class AB amplifier, a linear analog Class AB amplifier. The switching part makes a voltage that follows the audio signal that allows the amplifier to run cool and produce a lot of power without strain. That's what my switching power supply does. I call it the tracking down converter.
And that's different than what the actual amplification electronics are doing.
Exactly. The actual amplification electronics is a class of very, very high-end Class A or Class AB amplifier. Excuse me.
And one last question, because we're almost out of time, but a related question is, what are your thoughts on solid-state amplification versus tube amplification?
I grew up with tubes. I love vacuum tubes. They glow in the dark. I have a wonderful warm feeling when I listen to my music with vacuum tubes. Again, go back to the stereophile challenge, and you can see that a vacuum tube amplifier and a solid-state amplifier can be made to sound virtually indistinguishable. That's the reality of it. However, when I listen to vacuum tube amplifiers, I go, there's a magic here that I adore and love, and I'm not about to give it up. So I have both amplifiers in my listening room. I have vacuum tube amplifiers. I have solid-state amplifiers, our latest solid-state amplifiers, and they both sound stunning to me. I'm very, very happy with both of them.
Can you describe at all what the difference might be if they measure virtually identically, as you've talked about in the amp challenge? What is that magic?
Oh, here's one of the magic. If we listen to a vacuum tube amplifier, when the vacuum tube amplifier produces a signal, it makes the loudspeaker move. The loudspeaker sends sound waves into the room. The sound waves bounce off the wall, and they come back to the loudspeaker. And like a microphone, they make the loudspeaker move. That loudspeaker motion makes a little voltage, just like a microphone would. That voltage is fed back around the amplifier's feedback loop back to its input. All amplifiers have two inputs. One, this audio signal that comes from the outside world. The other is the audio signal that is the feedback signal. Both of those signals are the same. They're the same amplitude, same frequency response, everything. So what happens on a vacuum tube amplifier, the amplifier makes another sound that's related to the sound that it heard. In other words, the amplifier is able to listen to the room because it's hearing reverberation, echoes, time delays, all of the components associated with the venue. So the loudspeaker speaks, and the room speaks back to the loudspeaker. The amplifier hears it by the signal going around the feedback loop, and out it comes again. And it gives...
It's delayed by some amount of time, right?
It's not delayed by much. The real delay is the acoustic delay from the...
Exactly. That's what I'm talking about, yeah.
Yeah, and it's delayed. Exactly. And that delay makes it sound spacious and big to our ear-brain system. We love sounds that have ambience and echoes and stuff like that. So,
but don't solid-state amps do the same thing?
No. A solid-state amplifier, its output impedance is so low that when it tells the speaker to move, the speaker sends the wave out, bounces off the wall, comes back, and the solid-state amplifier will not allow the speaker to move in response to the sound wave coming back and hitting it. So
how can the amplifier tell the speaker how to move?
The amplifier tells the speaker how to move initially.
Right.
But then the amplifier shorts the speaker out so that the speaker can't move on the back wave. It's said the amplifier is said to have a very low output impedance, so the speaker can't move. In other words, that's all it is. It shorts the speaker out, basically.
So the vacuum tube amp has a somewhat higher output impedance.
Exactly, and that higher output impedance is one of the things we hear when we listen to vacuum tube amplifiers. It's one of the things that makes a vacuum tube amplifier sound so enjoyable and so nice and so spacious.
Wow, wow, wow. Well, that's absolutely fascinating. I've had a wonderful time this hour, but unfortunately, we are out of time. So I want to... will you come back? Will you come join me again at some point?
Of course I will. I will come back whenever you like.
I sure appreciate it. Thank you so much, Bob Carver. You can see his company's website at sunfire.com. And I certainly encourage you to go check out what Sunfire is up to these days. My online homes are ultimateavmag.com and hometheatermag.com, and you can email me at scott@twit.tv and follow me on Twitter at htgeekscott. Next week, my guest geek is scheduled to be Kevin Collins, a media center maven and formerly the HD DVD guru at Microsoft. So I'm certainly going to be asking him about that, as well as plenty of stuff on media servers. So I hope you'll tune in. Until then, geek out.